Hi, this is part 3 of my lecture of ancient solutions on geometric flows. And if you recall, in lecture 2, we spoke about the classification of two convex uniformly two convex ancient solutions to the mean curvature flow, which are also non-collapsed. And then we also saw that Hasselhofer, Hershkovich, and Brian White independently, they constructed solutions that we call the ancient ovals, and which are not the spheres, and they are not self-similar solutions, right? So if you recall, so they look something like this. They look cylindrical in the middle, and around the tips, they look like the ball solitons. And then what we did in the lecture 2, under the assumptions of rotational symmetry, we proved that if this solution is not the sphere, then it has to be this ancient oval which is constructed by Brian White and Hasselhofer and Hershkovich independently. Or in other words, right, so if we consider like uniformly two convex non-collapsed ancient solutions to the mean curvature flow which are closed and which are not the spheres, then we proved that they have to be the unique solution constructed by Hasselhofer, Hershkovich, and Brian White independently under the assumption of rotational symmetry, right? But we also have a theorem with Angenent and Daskalopoulos, which says let MT, T goes from negative infinity to capital T, be an ancient oval that is uniformly two convex, then it is rotationally symmetric. So remember, in our definition, ancient oval was just like a non-collapsed and convex closed ancient solution to the mean curvature flow. And here we are assuming that it is uniformly two convex. And in the definition of the ancient oval, it's also included that it is not self-similar, because if it is self-similar, then we know the solution has to be a sphere. Right? But here now we start with an arbitrary ancient oval, and we prove that it has to be rotationally symmetric. So due to our result that we discussed from last time, we have the uniqueness. Okay, so here I will just say that we adapt Brendle-Choice arguments in a non-compact case to our compact setting. And one thing that we show first is the following. If xj is in mtj and tj goes to negative infinity, then the sequence of rescalings, which I will call qj times f of tj plus tqj to negative 2 minus xj. So we rescale around the sequence xj, tj. So we start with an arbitrary xj in mtj and an arbitrary sequence tj that goes to negative infinity. Then we rescale by qj, which is just the mean curvature at xj, tj. And then we take the limit. So we can take the limit. So this subconverges to either the ball soliton or a round cylinder. Right? So this means that if I take a limit around an arbitrary sequence of points xj and tj and I rescale by the mean curvature, then it always converges to either the ball soliton or the round cylinder. And both of these solutions, both of these limits are rotationally symmetric. So which means that, right, the solution, our ancient solution is very close to something which is rotationally symmetric. And we will use that to actually prove that the solution itself has to be rotationally symmetric. And to do that, we use neck improvement theorem, which is developed by Brendle and Choi in their paper. And I will say that we focus on n is equal to 2 for simplicity, though like we can extend this also, of course, to the higher dimensions. Okay, but I'm just going to focus in this talk at n is equal to 2 for simplicity. Okay, so here is the definition. K, which is a vector field in R3, is a normalized rotation vector field if there exists a matrix S in O3 and a point Q in R3, so that K of X, which is SJS inverse of X minus Q, where J is just the matrix of rotation in R3, so 0, 1, 0, negative 1, 0, 0, 0, 0, 0. Okay, so we will say, right, that K vector field is a normalized rotation vector field if this is satisfied. Okay, and then here we have another definition which says that we say that X bar T bar is epsilon symmetric if there exists a normalized rotation vector field in R3, so that the absolute value of K dot nu times H is less than epsilon in a parabolic neighborhood. Okay, and this parabolic neighborhood I'm going to call P X bar T bar, and then 10 over H of X bar T bar, and then 100 over H squared of X bar T bar, right? So this is like, so everything is of this, on a scale of the mean curvature at a considered point, and I'm just gonna now define for you what this parabolic neighborhood for us means. So this parabolic neighborhood, which I'm gonna call P X bar T bar, and then let's call it R comma capital T, is a ball of radius r centered at X bar cross the time interval T bar minus T up to T bar. Okay, so that's the definition of this parabolic neighborhood that we have in this definition. Okay, so this is what we, when we say that the point is epsilon symmetric. So it's epsilon close to being something which is rotationally symmetric. And so I will just say, like, first in words, and then I will make it a little bit more precise, that this neck improvement theorem that we adapt to the compact case from Brandler-Choi's paper actually says that the neck becomes more symmetric under the evolution. Okay, and this theorem can be applied whenever we have a solution to mean curvature flow, which is close to a cylinder on a sufficiently large parabolic neighborhood, right? So being close to a neck means that after rescaling, you are actually close to a round cylinder, right? So like the theorem that they develop doesn't work only for ancient solutions, but for anything which is in a large parabolic neighborhood close to a cylinder, right? So I'm just gonna write here. So neck improvement theorem, which says the following: there exists L big and epsilon 1 small, so that if every point in this parabolic neighborhood around x bar t bar of size L over h of x bar t bar, comma L squared over h of x bar t bar squared lies at the center of an epsilon 1 neck and is epsilon symmetric, then x bar t bar is epsilon over 2 symmetric. Right, so this just tells us that if we are very close to a round cylinder on a sufficiently large parabolic neighborhood, everything is of course on a scale of the mean curvature, right? So which means that every point in this parabolic neighborhood lies at the center of an epsilon 1 neck and is epsilon symmetric. Then for the point x bar t bar, you can actually say that this is epsilon over 2 symmetric. And then you have the similar theorem around the tips where your solution is close to the ball soliton, which is also rotationally symmetric. So you also have to prove the cap improvement. Oops. Cap improvement theorem in the tips, at the tips, where we have closeness to a rotationally symmetric ball soliton. And then you have to iterate these two theorems to actually prove that your solution is rotationally symmetric. And here, like in the proof of that, in the proof of this iteration, it is important that you have an ancient solution, so which means that the time can go all the way up to negative infinity. And this will give you rotational symmetry, right? And now I'm just gonna write the theorem. Okay, so the combined theorem of Brendle and Choi, and then Angen and Daskalopoulos and myself, says the following thing, that the only non-collapsed, uniformly two convex ancient solutions are Sn, the ancient oval, that is constructed by Hasselhofer, Hershkovich, and Brian White independently, right? Round cylinders, and the n-dimensional ball soliton, right? So this is the complete list. And now let's just like briefly discuss application of our techniques in other people's works. Okay, so Choi, Hasselhofer, and Hershkovich, they proved the same classification as above, okay, in dimension 3, assuming low entropy assumption. Okay, here by entropy, I just mean like a quantity which was defined by Kolding and Minkowski, but I don't want to go into the details. But basically what is like the big achievement of this theorem is that they don't assume any convexity assumptions, and they don't assume any signs on the principal curvatures. All what they assume is the low entropy assumption, which basically more or less means that as you go backward in time, you are very close to a round cylinder, okay, after rescaling. And they managed to prove the classification result under like much weaker assumptions, but they rely on our theorem, which I stated earlier. Okay, and then Choi, Hasselhofer, and Hershkovich, they actually extended their theorem to higher dimensions together with Brand-White. Okay, and they proved the classification in higher dimensions, assuming the parabolic blowdown must be around cylinder. Okay, so in higher dimensions, right, all what they assume is that the parabolic blowdown must be around cylinder, which means that as you go backward in time, as time approaches to negative infinity, after rescaling, you are like closer and closer to around cylinder, which this low entropy assumption in dimension 3 also implies, right? And so I will just say that they used our classification, our result of classification of ancient solutions, once they established under their hypothesis rotational symmetry and smoothness of a solution, right? And of course, convexity. Right, so they first establish those assumptions that we impose in our theorem, and then they use our classification result. And then I will also say that Choi, Hasselhofer, and Hershkovich, Brand-White, in the same paper, they used their classification result to prove the mean convex neighborhood conjecture for next singularities. Okay, and it says the following: if the mean curvature flow develops the next singularity at x naught t naught, there exists a space-time neighborhood around x naught t naught, right, of some macroscopic scale, let's say of size delta greater than 0, in which the mean curvature is actually strictly positive even, right? So this means that like if they know that their solution to the mean curvature flow develops the next singularity, right? So which means that the singularity model is around cylinder, right, at point x naught t naught, then there exists the parabolic neighborhood of size delta, not of the scale of the curvature, but of size delta, which means of macroscopic scale, in which you can claim that your mean curvature is even strictly positive, even bounded away from 0, right? And then I will just also mention the result of Chodosh, Choi, Mantoulidis, and Schulze, where they consider low entropy surfaces in dimension n is equal to 2 or 3. Okay, and they prove that they can be perturbed so that their mean curvature flow has only spherical or cylindrical singularities. Right? So this means that they prove that these are sort of generic singularities, spherical and cylindrical singularities. So if you start with any mean curvature flow which is closed, they say that you can perturb it so that the mean curvature flow starting at the perturbed like surface develops only spherical or cylindrical singularities. And in like to prove that, they also use uniqueness of ancient mean curvature flows that lie on one side of asymptotically conical or compact shrinking solitons, right? And they also use our techniques for that, right? And the last thing that I want to mention is the result of myself and Schulze, where we again use the results in Choi, Hasselhofer, Hershkovich, and Brian White paper to show stability of neck pinch singularities. Okay. So what I mean by that is that if you start with a mean curvature flow that develops only finitely many neck pinch singularities at the first singular time, then the mean curvature flow starting at any sufficiently small perturbation of M0 can also develop only neck pinch type of singularities at the first singular time. Right? So if I start with something has only finitely many neck pinch singularities, there exists a neighborhood around that surface, so that the mean curvature flow starting at any surface in that neighborhood also can develop only neck pinch type of singularities. Okay, so these were like some applications of our techniques that we developed in the papers with Angen and Tentaskalopoulos. And then in the remaining time, I'm gonna just also tell you that we also managed to apply similar techniques to prove the uniqueness of kappa non-collapsed ancient solutions to the Ricci flow. Okay, so I'm gonna now tell you something about the Ricci flow results. Okay, so MG0 is a compact Riemannian manifold. And then we also evolve this by the equation -2 Rij, where Rij is the Ricci curvature, and where we start at time 0 with this metric G0. So this is called the Ricci flow equation. And then ancient solution, similar to the mean curvature flow, is the one that exists from time -infinity up to some time capital T. Okay. And so now, like when n is equal to 2, then the Ricci curvature is just 1/2 the scalar curvature times Gij. And Hamilton and Chow, they also proved that after normalization, the flow exponentially converges to a round sphere S2 as time approaches to plus infinity, right? So this is a result that holds only in dimension n equals to 2, so which means that if you start with a closed, if you start with a closed manifold with the Riemannian metric on it, and if you evolve it by the Ricci flow, then it will develop only spherical type of singularities, which means that after normalization, the normalized flow will exponentially converge to a round sphere. Right, and then what is like interesting, that holds only in dimension n is equal to 2, that this flow is conformal, right? So hence, I can write the evolving metric as a conformal factor times this round metric on S2, right? Which is the limiting round sphere that comes from this theorem, right? And this round metric on S2, I can write as d psi squared plus cosine squared psi d theta squared, where psi and theta are just the coordinates, global coordinates on S2. Okay, so now in dimension n is equal to 2, the Ricci flow equation, which is in general a system, is equivalent to the scalar equation, right, of the conformal factor. So ddt of u is the Laplacian, where the Laplacian is with respect to the round sphere, log u minus 2. And then you want to classify ancient solutions to this PDE, basically. Okay, and let me tell you the candidates. Okay, the first one is the contracting spheres. Okay, where u is just 2 times negative t, right? We are taking capital T to be 0 here. And the second is u, it's a rotationally symmetric solution, which depends only on psi. And this is given by A of t plus B of t sine squared psi to negative 1, okay, for t less than 0, where A of t and B of t are very explicit functions of time, right? So you can write them down explicitly. So this is like the explicit solution, and this solution here is called King-Rosenau solution. Okay, it's like the analogous solution to this ungenant oval, like in the curve shortening flow that we discussed in the first lecture, which was also given by the explicit formula. And then, like in the curve shortening flow, together with Daskalopoulos and Hamilton, we actually prove that the only ancient solutions to Ricci flow on S2 are 1 or 2. Okay, and like in the curve shortening flow, this other solution, in like the second one, which is not a soliton, is actually given by the explicit formula. So we could play with some monotone quantities that we could check, that we could actually check by hand, that they were vanishing on the solution whose uniqueness we wanted to show, right? So we could play with various monotone quantities, and the main idea here was to consider the quantity q of x, y, and tau, which is v bar times v bar xxx minus 3 vx yy squared, and then plus v bar y minus 3 v bar xyy squared. Okay, and v bar is just v bar is just like the conformal factor which corresponds to, okay, so I'm just going to say that v is just u to negative 1, and v bar is actually corresponding to this v after stereographic projection of S2 on top plane. Okay, and then this quantity q can also be like seen as v bar times v bar z squared, where z is x plus iy, right? So here we are just taking the three complex derivatives. And what we show, right? So we show the monotonicity of this quantity along the flow, actually the maximum of this quantity along the flow. And by using that, we show that if a solution is not a sphere, we show that q has to be identically equal to 0 for every t, right? And then, since q is identically equal to 0, we can just solve, like, and explicitly compute what v is, right, from here. So you see, like, since we knew the explicit formula for the solution, we could play like that. Okay, but now the question is, what happens in higher dimensions? I'll just briefly tell you the definition of a kappa solution. Is an ancient Ricci flow solution, which is non-collapsed with bounded and non-negative curvature. Right? And in dimension 3, for example, in dimension 3, we have Hamilton-Ivy pinching estimate, which like immediately implies that every like this ancient solution has the bounded and non-negative curvature. So in dimension 3, these are not really assumptions, right? And we will actually focus on dimension 3. Right? So in dimension 3, the only assumption is that we consider an ancient solution which is non-collapsed. And I will just say that Perelman constructed a non-collapsing rotationally symmetric ancient solution on S3. Okay, and I will just say the construction of these solutions is very close to the construction of the analogous solutions that we saw that they exist in the mean curvature flow and which were constructed by Brian White and then later by Hasselhofer and Hershkovich independently. And in the case of the mean curvature flow, you can like perform the similar type of the construction, just you have to apply different arguments to justify certain things, but the solution will in the middle after rescaling look like a round cylinder, and after appropriate rescaling around the tips, it will look, so here we will have S2 cross R, and here we will have a three-dimensional Bryan-Soliton. I'm not gonna go too much into details, but this is just the Bryan-Soliton, okay, which is a steady soliton or a solution to the Ricci flow equation, which moves only by diffeomorphisms, right? So the shape of this solution doesn't change, and it just moves by diffeomorphisms. Okay, so right, so satisfies the equation Rij is nabla I nabla Jf for some potential function f, and the diffeomorphisms along which this solution moves is one parameter family of diffeomorphisms which is generated by this vector field gradient f, right? And I will just say that Brandle proved that if you have m g of t, which is non-compact, three-dimensional, ancient kappa solution, then it is isometric to either family of shrinking cylinders or the Bryan-Soliton. This Bryan-Soliton is the analogous solution to the ball-soliton that we discussed in details in the mean curvature flow, right? So this is like for the Ricci flow, this is just a solution that is rotationally symmetric and moves by diffeomorphisms and is very well understood, even though it's not given by the explicit formula, right? So Brandle covered the case which is non-compact, right? So he did the classification in the non-compact case. And then the last theorem that I want to mention is a theorem of Brandle, Daskalopoulos, and myself. And then independently was also obtained by Baumler and Kleiner, and which says that every three-dimensional closed kappa solution m g of t needs to be rotationally symmetric. Okay, And since we already briefly discussed similar proof for the mean curvature flow, I will just say to prove this, we adapt Brandless ideas of proving rotational symmetry in the complete non-compact case of the Ricci flow. And similarly as to the mean curvature flow, we also show that for every sequence xk and tk, as tk approaches to negative infinity, if we rescale the flow by the scalar curvature at the points xk, tk, and take the limit, then in the limit we either see a shrinking cylinder or the brine soliton, right? Because recall that our solution looks like this, again, right? It looks cylindrical in the middle, and then around the tips, it resembles the brine soliton, right? And what you prove that, like, if you take any sequence of points and rescale by the scalar curvature, the limit will be always one of the two, either the cylinder or the brine soliton, and that is actually used to prove the uniqueness. Once you know the rotational symmetry, you can write G to be ds squared plus psi squared st gs2, where this s is a distance function from the equator, right? S is a distance function from the equator, and this psi is just the radius, right? It's just the radius of a cross section of distance s, or of distance s from the, which is at the distance s from the equator. And then the Ricci flow in this case is equivalent to the equation d dt of psi is psi ss minus 1 minus psi squared over psi, right? But like this s depends on t, so dds and ddt in this case here do not commute. Okay, so just check the time. So in the last 2 minutes, I'm gonna just tell you the theorem that we proved, right? With Brandle, Daskalopoulos, and myself, which says let S3 G of t be a compact kappa solution to the Ricci flow. Then it has to be either round S3 or the Perelman's solution. Okay, that was conjectured by Perelman in the first of his ingenious 3 papers, where he proved the Poincaré conjecture, and now we managed to prove it again in the series of papers that in the closed case, the only kappa solutions in dimension 3 are either the round sphere or the Perelman's solution. Because right in the previous theorem, like which is written in purple here, we know that such solution has to be rotationally symmetric, and hence you can work with this PDE. And what we do first together with Angenent, we show unique. Okay, so the first thing we do, we show unique match asymptotics like we did also in the mean curvature case, and then we prove coercive weighted estimate L2 estimates on W, which is U1 minus U2 in the cylindrical and the tip region. And then we combine them to show that W has to be identically equal to 0 up to translations in time and dilations. Okay, so this is like the theorem that we have. Brandle completed the theorem in the complete non-compact case. And now what would be the interesting question here is, what about higher dimensions? Okay, because you have the analog of Perelman solutions also in the higher dimensions. Okay, so under what conditions you can actually claim that the only kappa solutions in the higher dimensions have to be either the round sphere or the Perelman solution, right? So if you just put some curvature assumptions, it seems it's not enough, because there is a group of people that constructed counterexamples, right? So like maybe like one could conjecture that the right assumption would be like in the mean curvature flow, that if the parabolic blow down is a round cylinder of like of a kappa solution, right, and is not, then it has to be the Perelman's solution, right? If we manage to prove something like that, then we would be able to also have a nice classification result in higher dimensions. And I would like to thank you for your attention, and I'm gonna now see you soon. Bye.